video, we're going to discuss a different kind of application of the derivative. So we've talked about using the derivative to solve optimization problems, finding maximum and minimum values. We can also use the derivative more in its original sense of what it actually means. When we defined what the derivative was, we defined it as the instantaneous rate of change of a function, or geometrically speaking, you can think of it as the slope of the tangent line to a function if we were to look at the function's graph. So going along that line of thinking about the derivative as representing change, we're going to talk about what we call marginal change and then define what we call a differential. So calculus and the derivative, specifically, what we've been looking at for the past several sections, is often used to make approximations. So not exact values, but approximations of how quantities change in relation to one another. So when we use the Leibniz notation dy dx, we refer to that as change in y with respect to change in x. We're talking about how y is changing, how our outputs are changing, as x, our input variable, is changing. So based on how the derivative is defined, that is essentially what it means. It's change in one quantity with respect to another. So we're going to talk about another way you can use the derivative, thinking about this in terms of change. So let's talk about an application first. So when a company, for instance, considers making a change in production level, how much they produce and sell, they'll typically analyze the effect on cost, how much it's going to cost to foreseeably increase production level, the change in revenue, if they could expect to make more, and then most importantly, the change in profit, the bottom line. Do the gains in revenue offset the gains in cost? If so, then the profit is benefited and it may be beneficial to increase the production level. In order to analyze these three values, we can use what we call marginal cost, revenue, and profit. So in general, if we want to know how cost or revenue or profit is changing as we change the production level from, we'll just say most generally, x to x plus 1. In other words, we're going from an unknown quantity to one additional unit. So say x were 20, that means we're producing 20 units. What would it take to produce 21 instead? So we're looking at stepping up production by exactly 1 unit. So if we wanted to analyze what's going to happen to increase production by 1 unit, we have a couple of different options for how we would perform that analysis. So option 1, we'll just talk about cost, but keep in mind revenue, profit, same kind of thing. Option 1 would be to find the value of cost for our current production level, find the value of cost for the proposed increase in production, and then subtract the two values. So this would give us the exact value for the amount of change in cost to go from producing x to producing x plus 1 units. So this is the total cost for producing x units. This is the total cost for producing x plus 1. The difference between the two tells us how much cost will increase to go from one to another. So this will give the exact amount of change to go from one level to the next. But in a lot of cases, it may be really tedious to calculate something like that, particularly if your cost function, or again, your revenue or profit function, is complicated. You're performing a function evaluation twice, and then you're having to do a subtraction, which may be a little bit cumbersome. And then why would we think of it as cumbersome if that's our only option? We have a shorter option that's going to allow us to avoid the algebra that would require there, something that would be a little bit more straightforward. So option 2 is to recognize that the change in cost, not total cost, but if we're just interested in the change to increase production by 1 unit, the change in cost is closely related to the derivative. Because remember, the derivative tells us how a particular value is changing with respect to another. So if we want to think of the amount of change in cost, that's the value we're representing the change in, with respect to a change in X, the change in the production level, the derivative essentially represents that. So the derivative, C prime of X, is closely, it's approximately the same thing as what it would take to subtract these two values. So the difference between these two values is the exact amount of change to go from one production level to the next, to add one more unit. But the derivative, just that one expression, is approximately the same thing as if we were to take our new proposed cost and subtract the cost at the current production level. And again, this yields an approximation of the change, but it's usually easier to find, and it's typically so close to the actual value that it's going to be usable. It's not going to make a difference whether we go exact or approximate. The approximation is going to be fine, and then of course it's going to be faster because we only have to do one evaluation. So when we use the derivative to estimate change like this, rather than looking at exact values but to use the derivative to approximate, what we're finding is what we call marginal cost, or again, revenue or profit, same idea, same idea. So to go from producing and selling X units to producing and selling X plus 1 units, in other words, stepping up production by exactly 1 unit, we have the following three definitions for our marginal values. So marginal cost is the approximate cost of producing just the X plus first unit. So we have a total cost for producing X units. The additional cost we add on to produce the next unit is given by our derivative. So the derivative of cost is approximately the same thing as the difference between the total cost for our X plus first unit minus the cost for the previous unit where we're currently producing. Or alternatively, depending on how we want to use this relationship, this approximate relationship, the total cost of producing at that new production level is also approximately the same thing as our derivative plus the total cost at our current production level. How do we get from one to the other? Well, if you imagine just taking this relationship, which makes sense, right? The derivative represents an amount of change. This is the amount of change for 1 unit exactly. So to go from X units to X plus 1 units, the derivative tells us how much it's going to take to get there. If we were to rearrange this relationship, just add C of X and move it over, then the total cost for the higher production level is going to be the total cost for where you currently are plus the value of the derivative, and this is what we call the marginal cost. That's the marginal cost, the cost for producing 1 additional unit more than where you're currently producing. And revenue and profit, exact same thing. So the approximate revenue from selling unit X plus 1, that 1 additional unit, is given by our derivative. So the derivative of revenue is approximately the difference between the total revenue for our higher production level minus the total revenue for our current production level with a difference of 1. Or again, same kind of alternate relationship. If we want the total revenue for increasing production, then we can say that the total revenue for producing 1 additional unit is approximately the same thing as the derivative, our marginal revenue, plus the current revenue at our current level of production. So where we're producing currently, how much revenue we make for that, plus the amount of change to go from our current level to 1 additional unit. And then again, same thing with profit. So the marginal profit, aka the derivative, is approximately the same thing as the exact difference in profit going from X units to add on an additional unit. Or again, alternatively, the total profit for producing that 1 extra unit is approximately the same thing as the marginal profit at the current production level plus the total profit at that current production level. So essentially this boils down to, if we want to estimate what it would take to add on 1 unit to our production level, the derivative is going to tell us what that's going to look like. So if we were to evaluate the derivative of our function at the current value of x, the value of the derivative at that current level tells us how much we would have to add on from the current level in order to get to the cost, the revenue, the profit for that level where we increase production by 1 unit. So let's look at a couple examples using these marginal values. Okay. So given a cost function of 62x squared plus 27,500 and a revenue function of x cubed minus 12x squared plus 40x plus 10, and in both cases x is the number of units produced and sold, we want to find each of the following. So first thing we want to find is the total profit defined as P of x. Profit is our bottom line. We want to analyze the profit. If we know what the representation is for cost and for revenue, profit is always defined as the difference between the two. So profit is going to be revenue minus cost. And so we just evaluate that with our particular expressions. So revenue is cubic, so x cubed minus 12x squared plus 40x plus 10, and then we're subtracting cost, so minus 62x squared plus 27,500. Okay, so now we're just combining our like terms. So we have 2 quadratic terms, we have 2 constant terms, and so the cubic and linear term, they just kind of hang out. So x cubed, now we have negative 12x squared minus 62x squared, so negative 12 minus 62, that's going to be negative 74, so negative 74 x squared plus 40x, and positive 10 minus 27,500, so 10 minus 27,500, negative 27, 490. And you can put the comma in, you can leave it off, it's your choice. So this function tells us what our profit is going to be based on our level of production, the number of units, x. So the next thing we want to find is the total cost, revenue, and profit from producing and selling 50 units. In other words, when x is 50. So cost for selling 50 units is going to be our cost function evaluated with a value of 50. So 62 times 50 squared plus 27,500. And of course we can just plug that into the calculator if desired. So 62 times 50 squared plus 27,500. And that's going to be 182,500. We're talking about cost, so currency. 182,500. Now the revenue for producing and then selling 50 units, sub into our revenue function. So 50 cubed minus 12 times 50 squared plus 40 times 50 plus 10. Okay, and sub it in again, plug it into your calculator, evaluate. So 50 cubed minus 12 times 50 squared plus 40 times 50 plus 10. Okay, so 97,010, and again we're talking about dollars. So 97,010. And then what about our profit? Now we have a couple of different ways we can determine what our profit would be. Either we can use the profit function or revenue minus cost. Remember, that is profit. So let's determine it that way. So profit of 50, profit for producing and selling 50, is going to be the revenue at that production level minus the cost at that production level. So 97,010 minus 182,500. So 97,10 minus 182,500. And now we're again talking dollars, but it's negative. So negative $85,490. In other words, at this production level, this company is not profitable. The profit is negative. And why is that? It's because the costs exceed the revenue. So the amount you're making for producing and selling this much is not enough to cover the cost. So we're in the red in this case. So the next question is, what are the marginal cost, revenue, and profit when 50 units are produced and sold? And we want to interpret what this means. When we find these values, what do they mean? Well, marginal means, number one, we're starting by taking the derivative. So marginal cost is represented by the derivative. So C prime of X, let's go back and look at the cost function. Okay, so we differentiate the first term, bring down the 2, so 62 times 2 will be what, 124, and then decrease the exponent by 1, so 124x. Okay, C prime of 50 is the marginal cost when 50 units are produced and sold. So C prime of 50 is going to be 124 times 50. And again, we can sub that into the calculator. 124 times 50, 6,200. What's the unit here? The unit is still dollars. So 6,200. Okay, what about revenue? So marginal revenue, again, that's going to be the derivative. In this case, the derivative of the revenue function. So let's go look at that. So cubic function, okay, so the first three terms will stay when we differentiate. So 3x squared, 24x, or negative 24x, plus 40. So 3x squared, negative 24x, plus 40. And then we want the marginal revenue at 50 units. So 3 times 50 squared minus 24 times 50 plus 40. And again, we're talking about dollars. So 3 times 50 squared minus 24 times 50 plus 40, 6,340. And then our marginal profit, the derivative of our profit function. So there's our profit function. So 3x squared, bring down the 2. 2 times 74 would be 148, and then 40. So 3x squared minus 148x plus 40. And then the marginal profit at the production level of 50 units, sub that into our function, or specifically the derivative, and then plug it into the calculator. And again, we're still talking about dollars. So 3 times 50 squared minus 148 times 50 plus 40. And that's going to give us 140. Where does this come from? Well, look at the difference between the marginal cost and the marginal revenue. Marginal revenue exceeds marginal cost by $140. So profit still related to revenue and cost in the same way. So what do these values represent? Well, the marginal cost, revenue, and profit represent those values when we go from our current level of production to one additional unit. So these are the additional monetary values associated with going from 50 units produced and sold to 51. So if we were to produce that 51st unit, the 51st unit, just that one unit, is going to cost $6,200 to produce, roughly. Remember, this is an approximation of the change. So it will cost roughly $6,200 to produce. Our revenue will increase by roughly $6,340. And so the difference between the two means that single unit, to go from 50 to 51, that single unit will add $140 to our profit. So since this will increase our profit, and currently our profit is negative, producing 50 units, it would definitely make sense in this situation to increase production and improve productivity, improve profitability. So marginal cost, marginal revenue, marginal profit, again, they represent how much we would increase or decrease. It's possible the value could be negative. How much these values would change if we go from the current level of production to adding on one more unit. So it's the additional cost, revenue, and profit we have just associated with that one additional unit. And keep in mind, it's not going to be the same value if we were to go from 50 to 51 versus maybe 100 to 101. The amount of cost, revenue, and profit associated with each individual unit differs. The more we produce, in general, the cost is spread out across more units, so the additional cost of adding on another unit usually isn't as high. So we can't assume it's always going to be the same amount to go from one level of production to the next. It's going to vary depending on where we're starting and where we want to go. So let's look at one additional example like this. So suppose the daily cost in hundreds of dollars of producing X security systems is given by the following function. C of X is equal to 0.002 X cubed plus 0.1 X squared plus 42X plus 300. And currently, 40 security systems are produced daily. So the first question is, what is the current daily cost? Well, our current level of production is 40, so 40 units. This function tells us what our cost is based on how many units we produce. So the current cost is going to be C of 40. So let's evaluate that. So C of 40 is going to be 0.002 times 40 cubed plus 0.1 times 40 squared plus 42 times 40 plus 300. And again, let's just plug that into the calculator. So 0.002 times 40 cubed, okay, plus 0.1 times 40 squared plus 42 times 40 plus 300. Now that was a lot to type, so let me verify everything looks good. Okay, 300, 42 times 40, 0.1, 40 squared, 0.02, 40 cubed. Okay, that looks good. So there we go. What are we talking about in terms of units? We're talking about cost, so we're talking about currency. So $2,268. So that is the total cost for producing the 40 systems per day. So that's the total cost per day for those 40 systems. Okay, the next question, what would be the additional cost of increasing production to 41 systems? And we want here the exact change in cost. So if we want the exact change, we need to know what's the total currently, what would the total be for 41, and then the difference between the two is going to be how much cost is represented by just that one additional system. So we need the cost for the 41st unit. So same kind of idea, we evaluate this function, but now we're evaluating it with an input of 41 in order to represent the total at that increased production level. Okay, so let's sub that in. So 0.002 times 41 cubed plus 0.1 times 41 squared plus 42 times 41 plus 300. Let me double check it again. So 300, 42 times 41, 0.1 times 41 squared, and then 0.002, 41 cubed. There we go. So that's going to be $2,327 and 0.942. So if we're rounding to cents, that's going to be 94 cents. Now, this is not quite correct. I just noticed I missed something. What did I miss? Let's go back and look at the problem description. Hundreds of dollars. Cost is in hundreds of dollars. So how would that change these values? Well, if we're talking about 2,268, but that's in hundreds of dollars, if we were to multiply that by 100, well, that's going to give me the actual value. So it really means $226,800. That makes a little more sense, right? Those are some pretty cheap security systems if that's all it costs to make them, right? So what about the next one? Well, let's not round it. So let's use 2,327.942, okay? And we're multiplying that by 100. And so that's going to be the actual value there. And let's just round to the nearest dollar. So in this case, 232,794. So the question was, what would the additional cost be to increase production by 1 unit, to go from 40 units where we currently are to 41 units where we potentially could be. So the change is going to be the total cost for 41 minus the total cost for 40, and we just determined those values, and they're not 1,000, it's hundreds of thousands at that point. So cost for 41 is going to be $232,794, and then the current cost, $226,800, and then the difference between the two, $232,794 minus $226,800, and there we go. So $5,994. So we can think of this as the exact cost for producing the 41st unit. In total, it's going to cost us $232,794 to produce the full 41 units, but the additional unit, the one additional unit we add on to go from 40 to 41, this is going to be the cost of producing that one additional unit. So the next question is, what is the marginal cost when x is equal to 40? So as soon as I see marginal cost, I'm using the derivative. It's an estimate of this value. If this is the exact amount to go from 40 units to 41, the exact additional cost, the marginal cost is sort of a quick estimate of that. So why does it help? Well, it's going to save us some time, and I'll show you why. So we want the derivative of the cost function. So take our derivative, so bring down your 3. So 0.002 times 3 is going to be 0.006. That's going to be x squared. Okay, 0.1 times 2, bring that down, so 0.2x, and then 42. So plus 0.2x plus 42. And then if we evaluate our derivative, or marginal cost function, when x is 40, c prime of 40, 0.006 times 40 squared plus 0.2 times 40 plus 42. And again, this is going to be in dollars. We're talking about a change in cost, the amount of additional cost. So 0.006 times 40 squared plus 0.2 times 40 plus 42. And that's going to be 59.6, but not 59.6, right? Not $59.60. We're talking about hundreds. So multiply this by 100, 5,960. So 5,960. So compare these two values. This is the exact amount to go from one production level to one additional unit. This is a quick estimate of it, and it's relatively close. It's fairly close. It's just a difference of $34. And so as we continue to increase production, additional units typically cost less overall. So we would expect these values to be closer and closer if we were to increase production further. But why would we use this approach? Well, notice how much less work it took. Number one, when we took the derivative became a simpler function than the original function. And we also only had to do one function evaluation. So if we want the exact change in cost, notice we needed the new cost at the higher production level, the current cost at the current level, and then we had to subtract the two. So it is a multi-step process, whereas here we find our derivative, which then gives us a formula for calculating the difference for any pair of values to go from one unit to the next. And then we just evaluate our derivative at the current level, and that tells us how much we'd add on to go to the next level. So by finding the derivative here, we're essentially doing all of the real work for a problem like this, but we're finding a formula that's going to work not just for 40 to 41, but for any number to that one additional unit. So it is a major time saver, assuming we're okay with that slight discrepancy, which in most cases that discrepancy is not going to be a huge deal. So the last thing we want to do is use the marginal cost to estimate the daily cost of increasing production to 42 systems. What would it be in total to go to 42 systems? Well, the cost for 42 is going to be roughly the cost of 40, where we currently are, plus double that marginal cost. So if we know what the marginal cost is right now, if we were to add that on twice, that estimate for 40 will also be a pretty good estimate for 41, which would be the amount that we need to go from 41 units to 42. So if we were to just take this amount and double it, that is a pretty good, rough, but pretty good estimate of what it would take to go from 40 to 2 additional units at 42. And we know these values already. So C of 40 we determined was $226,800. So $226,800 plus 2 times our marginal cost, 5,960. So we can evaluate that. So 226,800 plus 2 times 5,960. And there we go. So that's going to be $238,720. Now I want to show you one additional way that you could calculate this so that maybe you get a value that's slightly closer. Another way to evaluate this using mostly values that we know would be to take the cost, the current cost at 41, since we did calculate that, and then add on just the marginal cost for 41. And we don't have that, but we can evaluate it because remember the derivative represents a formula for marginal cost regardless of the value we're talking about. So the total cost for 41, we determined that, so $232,794. 232,794 plus the marginal cost at 41. So imagine taking this formula and subbing in a 41. So what would that give you? So 0.006, 41 squared plus 0.2 times 41 plus 42. And that's going to be 6028.286. That doesn't sound right, does it? Why is that not right? What's wrong? Remember, multiply it by 100. So 6,028. There we go. That sounds better. And if we round to the nearest dollar, let's round up. So 6,029. And then let's get the approximation this way. So 232,794 plus 6,029. And that's going to be 238,823. So fairly close. Grand scheme, if we're talking about scale, if we're already up in the hundreds of thousands, differing by less than $100, these are both pretty good estimates. So either of these would be considered a relatively appropriate approach to calculating how much you would need in order to increase your production and what that would look like in terms of total cost. So marginal cost, definitely a great tool. Sure does beat having to do this kind of calculation twice. And again, we would have to repeat that calculation anytime we wanted to compare two additional production levels. Whereas with the marginal cost, all we need to do is one function evaluation right here, and that'll tell us what it would take to go from one level to the next. So the next thing we're going to talk about is something closely related to marginal change, which is what we call a differential. So right now, I'll go ahead and warn you ahead of time, differentials will probably seem just a little bit mysterious. Why we use them, how we use them is probably going to seem a little abstract, a little strange right now. We're going to need these later. So we're going to go ahead and introduce them now because they are closely related to this idea of marginals, which we definitely do have an application for. And we will revisit these later once we get to what we call anti-differentiation. So we can take a derivative, we can take an antiderivative. And what we're about to talk about here is going to be important when we get to that point. So with a marginal cost, revenue, profit, we're looking at what happens to increase production by 1 unit or increase whatever value by 1 unit. We can use a similar technique to estimate incremental changes, so an amount of change, for any two values that are close to one another. So not just one number and then one number up from it, so not just x and x plus 1, any two values that are close together. So I want you to recall the difference quotient, which we used when we originally defined the derivative. So the difference quotient, if we're talking about a function f, is defined as f of x plus h minus f of x divided by h. So the variable h was new. The variable h resulted from us changing notation. Rather than talking about x1 and x2, we talked about h, where h represents a small change in x. It represents just a small change to take us from one x value to another. Now we can also use what we call delta notation to represent an amount of change. So the variable h can represent change. If we're talking about x changing, then another way of expressing h would be using delta, which looks like a triangle. This is the capital Greek letter delta. So delta x is another way of saying change in x. So the amount of change that it would take to go from one x value to another. So what we're going to focus on using this amount of change is estimating the change in the values of function outputs. Think of it kind of like the cost at one value and the cost at another value. How do we compare them? Well, if we're just looking at 40 and 41 units, the marginal cost is going to help us. If we want to look at something a little bit more abstract, maybe not going directly from 40 to 41, but maybe 40 to just some unknown value, this is the strategy we're going to use. So if we want to estimate the change in the value of outputs, aka y values, not x values, then all of the following are going to be equivalent. I'm going to write out a long expression, a long equation that's going to take all of these different things, different ways of writing the same thing, and relate them to one another, and we're going to add in this new notation that we haven't used before. So when we're talking about slope, talking about average change, if we're looking at 2 points on the graph of a function, 2 x values, their associated y values, the original way of writing change, relating y's and x's, is going to be y2 minus y1 over x2 minus x1. So when you first talk about change, that's the expression for how outputs change in relation to how inputs change. Now we determined that these two expressions are equivalent. They mean the same thing, it's just different notation. So this is f of a further out x value minus f of our original x value. So y2 minus y1, the difference between the outputs. And then x2 minus x1, that's the difference, the distance between our two x values. Well, we call that h here. So these two expressions look very different, but they mean the same thing, just in a different notation. So that's the same thing as f of x plus h minus f of x divided by h. Well, if instead of h, we use this new notation, this delta notation, which is a way of saying change. You probably see this if you've ever taken a chemistry class. You've probably seen this delta before. Wherever we see an h, we could write a delta x instead, which again just represents how much we're changing to go from one x value to another. So this also could be written as f of x plus delta x minus f of x all over delta x. And then the simplest way to write it, which is again very similar to this original notation, change in y over change in x. Well, the delta means change in. So change in y over change in x. All of these expressions are equivalent to one another. They just vary the notation. But what I want to focus on here is where we ended up, this new notation, delta y, change in y with respect to change in x. The goal is to analyze what's happening with our y values, with our function values, specifically change in y. How are our y values changing based on what our original x value is, and then how far we want to go to get from one x value to another. So if we were to essentially throw all of this away at the moment and just analyze what we can see with this, just the change in y, these two numerators are going to have to be the same. Notice the denominators are the same. They're both delta x, so that means the numerators have to be the same as well. So if we look at these two numerators together, that is going to give us our expression for how we can approximate the change in y values if we're looking at this particular kind of situation where maybe we're not going from x to x plus 1, but an original x value to some unknown new x value. Maybe we jump by less than 1 unit. Maybe we jump by more than 1 unit. This is a more general approach to determining how our y values change regardless of how our x values change. So that expression is going to tell us how our y values change based on an amount of change in x. So using this relationship we have here, let's try an example just evaluating delta y. So we want to find delta y for each of the following. So suppose our function y is defined as y is equal to x squared. we want to determine what's happening, how are the y values changing when our x value is equal to 4. In other words, that's our starting x value. And then the change in x is 0.1. In other words, we're not jumping from 4 to 5 like we would if we were talking about marginal change, but we're going from 4 to just a little bit bigger than 4, just to 0.1 units higher than 4. What would the amount of change in y look like in that case? Well, we know that delta y, based on all of this we've now developed, delta y is defined as the same thing of f of x plus our change in x. So in other words, our function evaluated at the new x value, where we go from the original x and add on a little bit more, minus f of the original x value. And again, based on that relationship, based on those two matching numerators. Well, we know what x is, and we know what our delta x is, that amount of change, the distance between our original x value and the new one we want to generate. So let's plug in all of that. So f of x, which is 4, plus the change in x, which is 0.1, minus f of x, which is f of 4. So that's going to be f of 4.1. In other words, 4.1 is our new x value, minus f of 4, which is our original x value. Where do we get these values? Well, that's what our function is for. If we were to sub in these x values, square them, we'll get the associated output. So let's see what that's going to be. So f of 4.1 is going to be 4.1 squared, so 16.81, minus f of 4, which is going to be 4 squared, which is just 16. So the change in y to go from x equals 4 to 1/10 of a unit higher, which would be 4.1, is going to be 16.81 minus 16, which is 0.81. So that is the change in y as our x changes from 4 to a value that's 1/10 higher than that. That's our change in y. Let's try another one. So new function, new x value, new change in x. Notice here the change in x is negative, which means rather than increasing from 2 to a new value, we're decreasing to go to a new value. So again, delta y is defined, change in y is defined as our function value evaluated at the original x value plus the amount of change to take us to the new x value minus f of x. Sub in our values. So here x is 2, and then delta x is negative 0.1. So 2 plus negative 0.1, or you could write as minus 0.1 if you want, minus f of x, f of 2, the original x value. So this represents the new x value as we transition from 2 and change just a little bit. So what's it going to be? Well, 2 minus 0.1 is going to be 1.9. So f of 1.9 minus f of 2. And we get these values based on our function definition. So we're going to take our input and cube it. So 1.9 raised to the third power, 6.859, don't round. And then f of 2, 2 cubed is going to be 8. So I'm going to take the difference between the two, do that subtraction. So 6.859 minus 8, and that's going to be negative 1.141. So in other words, if we start at x equals 2 and transition to a value that's 1/10 less than this, then the associated change in y, the y values are going to decrease by negative 1.141 units. So just another way of expressing change using the same kind of idea as a marginal, but rather than talking about one unit specifically, changing from one unit higher to where we currently are, this gives us a way to talk about change regardless of how our x values are changing, regardless of how our inputs are changing. So let's take the expression and let's go one step further. So that alternate expression for the difference quotient that we just found, so f of x plus h minus f of x over h, we relabeled h as delta x. H is a small distance between one x value and another. Another name for that is delta x, change in x. So f of x plus delta x, same thing, just different notation, minus f of x, divided by, not h, but delta x. Now, the difference quotient we originally defined in order to define the derivative. So remember, if we were to take the limit of this expression as h goes to 0, we evaluate the derivative. Well, if we're changing the notation but applying the same principle, when we allow our denominator in this case, which is delta x, to approach 0, in other words, we're looking at the distance between the two x values, the change in x to go from one to another. If we allow that to go to 0, in other words, we take our two x values and we shrink the distance between them. We allow that distance to approach 0 so that those x values are infinitely close to one another until they essentially overlap. They lay on top of one another. If we were to execute that kind of procedure, then this expression, this version of the difference quotient, now represents the derivative. And essentially doing the same thing we did on the previous page, relating a bunch of things that are equivalent expressions representing the same thing just with different notations, then we're going to define what we call a differential. So let's set it up. So when we talk about the derivative, one way to write it, looks very similar to this in terms of how things are structured, something y over something x, except we used a d instead. Well, delta means change in, d means change in, but change in a different way. So dy dx means instantaneous change in y with respect to instantaneous change in x, or change in y with respect to instantaneous change in x. So if we're just looking at delta, that can be any change in x. X can go from any value to any other value, and we're associating the change in the y value. When we use this notation, which represents the derivative, we're specifically saying that the change in x has to be extremely small. It's infinitesimally small. In other words, we're taking it so that it's so small so that we're just looking at change at a single point on the graph, not between 2 points on the graph. Well, based on our new notation for the difference quotient and the idea that we would allow the limit to approach 0, the new way we could write that would be the limit as delta x goes to 0. Instead of h is going to 0, delta x is going to 0 of our new expression for the difference quotient. So again, just a different way of writing the definition for the derivative. Well, what is this? What is this? What was the other way of writing that? The other way of writing that was delta y over delta x. So in place of the expression for the difference quotient, we could substitute this expression, delta y over delta x. So taking the limit of the difference quotient would be the same thing as taking the limit as delta x approaches 0 of delta y over delta x, because they're equivalent. Again, different notations for the same thing. One y value minus another, aka change in y values. This, then, if we were to use the other notation for a derivative, this was our Leibniz notation. We also had the prime notation. So we also could call this, if we didn't want to use y's, we want to use f, we would call that f prime of x. All of these things are equivalent. But I want to highlight some specific things that are then going to lead us to these definitions for differentials. The idea behind a differential is if we take the derivative, which is a rate of change, one amount changing with respect to another, the differential allows us to decompose this rate of change and just look at change in y, just look at change in x, but not change in y and change in x like this, where we can talk about any amount of change, any amount of change. If we're talking about change and change in this notation, we're talking about not just any change, but infinitely small change. Change if you were to look at that single point on the graph where you're evaluating your derivative. So what I want to look at here, a couple different things. We know dy dx and f prime of x are going to be the same thing. And then another thing we can relate based on our denominators is dx and delta x. So all of these different things put together allow us to define what we're going to call the differential. Again, think of the differential. Individual differential means we're breaking apart our derivative into just dy, just dx, just small change in y, small change in x. So based on all of this that's all related to one another, dx and delta x are the same thing. They essentially mean the same thing. So the differential of x, what we're going to call dx, is going to be equivalent to delta x, just change in x, small amount of x, or small amount of change in x, we can also just call delta x. What we're more interested in is the differential of y at this moment. So dy is going to be related here. So imagine taking this, imagine writing an equation that just has that. So dy dx is equal to f prime of x. And if you were to take your denominator and move it over, you then have an expression for dy, what we call the differential of y. So dy, the super small change just in our y values, is defined as f prime of x times dx. dx is also the same thing as delta x. So we could also say that the differential is the same thing as f prime of x, our derivative, times delta x. And again, explaining why this matters, all of this seems very arbitrary at the moment. Explaining why this matters at this moment is not going to be all that productive, because again, we're going to use it a little bit later. It's the idea that it's related to this concept of the marginal, this amount of change, using the derivative to represent an amount of change, not as a rate of change, but specifically just an amount of change of one value. Here we're talking about an amount of change just in x. Here we're talking an amount of change just in y. But again, it's in terms of the derivative, what we mean by changing with respect to the derivative. Not any amount of change, but an infinitely small amount of change, something instantaneous. So let's work through a brief example for how we might actually use the differential. And again, we're going to revisit this later. We'll go into more detail later about what this means and why we need it. So consider the following function. F of x is equal to the square root of x. So y, f of x, same thing, both functions of x. So we want to find dy, the differential of y, when x is equal to 9 and dx is equal to 1. So what does this mean? It means our original x value is 9. The change in x is going to be 1. So that tells us how far we're going to get from 9 to our next value. And we want to know what's the differential of y, what's the change in y when we see this x value and its amount of change. So dy is defined as f prime of x times dx. Well, what are all these different things? Well, we need f prime of x. So let's go out to the side and I'm going to calculate f prime of x. Well, f of x is the square root of x. We know in order to differentiate that, we're going to convert that square root to rational exponent notation, and then we can use the power rule. So f prime of x is going to be 1/2 times x to the negative 1/2, which is the same thing as 1 over 2 root x. That's our derivative. Now, if we were to evaluate this at x equals 9, that's going to give us what we need to plug in. So f prime of 9, we can sub in a 9 to our derivative formula. So 1 divided by 2 times the square root of 9. Well, the square root of 9 is 3, and then 2 times 3 is going to give us 6. So 1 over 6. So that means dy is equal to the derivative evaluated at our x value, so 1/6, times dx, which in this case is 1. Now again, what does this represent? It represents our transition from the current x value to the next x value we want to go to. So in other words, we're transitioning from x equals 9 to 1 unit higher, x equals 10. So the associated change in y to go from x equals 9 to 1 unit higher is going to be 1/6 times 1, which is 1/6. And if we wanted an approximation of that, 1 divided by 6, approximately 0.1666 ... 7, so on and so forth. We would keep getting 6's, and it just repeats indefinitely. Now, next thing, we want to compare dy to delta y. What is delta y versus dy? Well, this is dy, okay, so dy is defined in terms of the derivative. What is delta y? Well, let's flip back over. We defined that as well. Delta y does not involve the derivative. It's just literal change in y to go from one function value to another. Okay, so dy uses the derivative. It uses the idea of sort of marginal change related to the derivative. Delta y just takes our function values and then transitions that way. So delta y, in this case, is going to be f of x plus delta x minus f of the original x value. That was our definition for this kind of change in y versus dy. Well, we know our x value, x is 9. What's delta x? Well, remember, dx and delta x, same thing. Change in x is just change in x. What differs is how we represent the change in y. So change in x is going to be dx, which is just 1. So that's going to be f of 9 plus 1 minus f of 9. So here we're relating change to the actual function, not to the function's derivative. So f of 9 plus 1, if we were to sub in 9 plus 1 to our square root formula, that's going to be the square root of 10, minus f of 9, which would be the square root of 9. Now, the square root of 9, we know we can approximate, or we don't need to approximate it. We can find that exactly. The square root of 10, we need to approximate. So, if we were to approximate that in the calculator, that's going to be the square root of 10 minus the square root of 9, which of course we know to be 3. And so that's going to be approximately 0.1623 if we were going to round. So we want to compare dy to delta y. We're comparing these two values. So this is change in y expressed in terms of the derivative, how the derivative represents change. So change in y as related to the derivative. So 1/6, about 0.166, so on and so forth. Delta y, again, doesn't use the derivative. We're just looking at function values, comparing one to another, taking the difference between the two. And so if we were to use the definition of change in y using delta and not d, our change is about 0.1623. So how do we use this kind of notation to determine something, to actually use it in a practical situation? Well, this kind of workup, this kind of estimation can be used to estimate an irrational number, something like the square root of 10. So the square root of 10, which we can think of as f of x plus dx, or delta x, that's going to be the same thing as f of x plus our change in x, which we could call delta x, or we could call, or not, excuse me, not delta, change in y, there we go, that's better, dy. Take our original x value, add on our amount of change, and that's going to give us the approximation. The approximation using the derivative is going to be more accurate in this case, because notice, if we were to just use 1/6, 1/6 doesn't require any rounding, whereas root 10 minus root 9 as an approximation automatically required rounding. 1/6 does not. So f of 10, which is the square root of 10, which is what we want to estimate, we're going to estimate that as f of x, which is the square root of 9, plus that amount of change, which was 1/6. So root 9 is going to be 3, 3 plus 1/6, 3 and 1/6, and if we want that in a calculator, 3 plus 1/6, 3.166, so on and so forth. And it just continues. So technically we want to write that as a 6. This is now an estimation of root 10. So if we didn't have the ability to plug root 10 into the calculator, how does this help us? Well, forget about this for a moment. Suppose you didn't have a calculator and you wanted to estimate what the square root of 10 is. Well, we recognize that the square root of 10 is pretty close to the square root of 9, and we know we can find the square root of 9. In fact, it's 1 unit away. The x values are 1 unit away to go from a number that's a perfect square to a number that's not, whose square root we want to estimate. So using the derivative, using this idea of the differential, this small amount of change, which we were able to determine exactly, that small amount of change we determined exactly as 1/6, we can take a function value that we know, add on that small amount of change to take us to a very good estimation of a function value that we don't know, something like the square root of 10. And this is similar to what your calculator is doing in the background. Your calculator doesn't actually do algebra the way you do algebra. The calculator does numerical estimation of a lot of values. So something like this is similar to what your calculator is doing in the background when it calculates something like the square root of 10. So this is just going to give us a way to approximate something like the square root of 10, something that is an irrational number, and something that we would otherwise just have to approximate in the calculator. So don't stress too much about this idea of a differential. Again, we're going to come back to this. Biggest thing to remember, these two relationships. If you can find these two relationships, you know how to find a derivative. You can find your individual values for your differentials. Marginals, on the other hand, definitely very applicable. We looked at a couple of application problems where we'd use those. And again, the general idea with a marginal is we're estimating how a y value, how an output would change as we change our x values by 1 unit. So if we increase our x values by 1 unit, the marginal change related to the derivative tells us how much our outputs would increase.